Somewhere in the dark of a temple that has stood for 2,000 years, there is a ceiling, and carved into that ceiling is a map. Not a map of land, not a map of roads or rivers, a map of the sky. When astronomers calculated which observations it encoded, which arrangements of stars, which positions the carvers were recording, they entered one of the most contested arguments in the history of science. Because some of what they found pointed not to the sky of the carver's own lifetime, but to observations that may have been accumulating for centuries, perhaps millennia, before the chisel ever touched the stone. Someone looked up, someone remembered, and someone carved what they saw into stone. Whether that memory stretched back further than we have been willing to believe, that is what this story is about. You do not need to hold on tightly tonight. You do not need to remember every name, every date, every disputed calculation. If you fall asleep somewhere in the middle, that is perfectly fine. The sky has been waiting for a very long time. It can wait a little longer. There are no easy answers in what follows. There are genuine discoveries and genuine mysteries and genuine arguments between careful people who have spent their lives trying to read what the ancient world left behind. What there is not, on any page of this story, is false certainty in either direction. The past does not owe us clean conclusions, but it does, sometimes, offer something better. It offers evidence, partial, contested, extraordinary evidence that someone, a very long time ago, was paying attention to the same sky you are lying under tonight, and that the observations they accumulated across generations, patient and careful and serious, were old enough, precise enough, and durable enough to be encoded into stone in forms we are only now learning to read. Some of the stones we will visit tonight predate every civilization we know by name. Some of them were built before writing existed anywhere on Earth. Some of them encode knowledge that was already ancient when the people who carved it were born. Settle in. Let your breathing slow. We are going a long way back tonight. Chapter 1. The Ceiling in the Louvre. There is a room in the Louvre in Paris where very few tourists stop for very long. It is not one of the famous rooms. It is not where the Mona Lisa hangs behind its barrier of bulletproof glass and its crowds of people holding up phones. It is quieter than that, less celebrated, and on the wall of that room, mounted in a frame that does not quite do justice to what it contains, there is a piece of stone that was cut from the ceiling of a temple in Egypt in 1820 and shipped across the Mediterranean on a French vessel and installed here, in this city of wide boulevards and old museums, where it has remained ever since. The stone is called the Dendera Zodiac. If you stand in front of it long enough, and if you know what you are looking at, it will begin to feel less like an artifact and more like a message written in a language that takes patience to read, addressed to someone the carvers could not have known, sent across a distance of time so large that the concept of it resists ordinary understanding. Close your eyes for a moment and try to picture it. Not the museum room with its careful lighting and its explanatory placard. The original, a temple ceiling in the desert, before any French ship arrived, before any European hand reached for a chisel, lamplight moving across carved stone, figures of animals and stars arranged in a circle on the ceiling above the inner sanctuary of the Temple of Hathor, placed there by craftsmen who believed they were recording something true about the sky and its relationship to the world below. That image is worth holding, because the first thing this story requires is honesty about what the ceiling actually is. And the honesty is more interesting than the mythology that has sometimes surrounded it. The Temple of Hathor at Dendera is not an ancient mystery in the sense that the word ancient is sometimes used to imply a connection to lost civilizations or impossible technologies. The structure that stands today was built during the Ptolemaic and Roman periods, the final centuries before the Common Era. when Egypt had already been ruled by the dynasty that Alexander the Great left behind. The ceiling from which the zodiac was cut dates to approximately 50 years before the Common Era. That is the mainstream scholarly consensus, established by Sylvie Colville of the French National Center for Scientific Research, who has spent decades studying the texts and carvings of Dendera in more careful detail than perhaps any other living scholar. The building is late. The carving is late. And yet the question that has kept researchers returning to this stone for more than a century is not how old the building is. It is something more interesting and more difficult. It is this. What data went into the carving? What observations were the craftsmen encoding when they placed these figures in these positions? And how long had those observations been accumulating before the chisel ever touched the stone? The night is quiet outside. Let that question sit for a moment before we go further. Because the Dendera zodiac does not simply show the sky of 50 years before the Common Era, it shows something more layered than that. It contains within it a system of 36 smaller star groupings called decans, a division of the sky into 10-day segments that Egyptian astronomers had been using to track the rising of stars before dawn for purposes of timekeeping and religious calendar keeping. The earliest texts referencing the Deccan system appear on the inside lids of wooden coffins dating to the Middle Kingdom period, roughly 2,000 years before the Common Era. Other references appear earlier still. The observations embedded in the Deccan tradition were not made by the craftsmen who carved the Dendera ceiling. They were inherited, accumulated across generations of watching the same sky from the same latitude, noting which star rose just before sunrise, on which morning of which season, building a picture of the heavens that required not individual genius, but collective patience, the kind of patience that measures itself not in years but in lifetimes. Imagine the craftsmen who made it, not as symbols of a lost civilization, as people, men who had trained for years under older men, who had trained under older men, still, learning to recognize the 36 decans by their positions, memorizing the order of their risings, understanding the relationship between the sky above and the calendar below, men who climbed scaffolding in a half-finished temple, working in lamplight that cast long shadows across the stone, carving figures they had been taught to carve, in positions they had been taught to recognize. They were not starting from nothing. They were the end of a very long chain. Sylvie Colville argues that the Dendera zodiac primarily reflects the astronomical knowledge of the Ptolemaic period in which it was carved, with the positions of the planets recorded at a specific date around 50 years before the Common Era. Other researchers, working with the same stone, have argued that certain elements of the composition preserve much older observational data, perhaps reaching back to the Old Kingdom or earlier, encoded into a tradition that was copied and recopied over 2,000 years before it was finally cut into this particular piece of sandstone. That argument has not been resolved. It may not be resolvable with the evidence currently available. What is not in dispute is the sophistication of what the craftsmen produced. The Dendera zodiac contains the 12 signs that will be recognizable to anyone who has ever glanced at a Western horoscope: Aries, Taurus, Gemini, and the rest, arranged in a circle around the central field of the stone. This is one of the earliest complete representations of the zodiac as a unified system that has survived from the ancient world. But the zodiac, as depicted here, is not a purely Greek invention imported wholesale into Egypt. It is a synthesis. The 12-sign zodiac had Babylonian roots reaching back to the first millennium before the Common Era. The Deccan system was distinctly Egyptian. What the Dendera craftsmen produced was a fusion of two traditions, a merging of Babylonian and Egyptian astronomical frameworks into a single image that reflected the intellectual world of the Ptolemaic court, where Greek, Egyptian, and Babylonian learning existed in conversation with each other. That fusion is itself a kind of time capsule. When you look at the Dendera zodiac, you are looking at the accumulated astronomical knowledge of at least 3 distinct civilizations, compressed into a single piece of stone. The man most directly responsible for its removal was a French engineer named Claude Louis Jolloy, who was part of Napoleon's Egyptian expedition and oversaw the cutting of the stone from the ceiling with, by the accounts of observers at the time, something considerably less than the care that a modern archaeologist would require. The ceiling of the temple at Dendera now has a plaster cast where the original once was. If you visit Dendera today, you look up at a copy. The original is in France. This matters because the Dendera zodiac is not just an astronomical document. It is also a story about what happens to the knowledge of one civilization when another civilization decides it wants that knowledge for itself, removes it from its context, and installs it somewhere else. The stone survived. The context did not, and some portion of what the carvers meant. The specific ritual significance of individual figures within the composition. The living relationship between the ceiling and the temple beneath it went with the context when the stone was cut. Scholars have been working to reconstruct that meaning ever since. The tools available to them have improved considerably in the 2 centuries since the stone arrived in Paris. Computational software can now reconstruct the sky above Dendera at any date in the past with an accuracy that would have been impossible for earlier researchers. The positions of the planets, the rising points of individual stars, the precise configuration of the zodiacal band, all of these can be calculated and compared against what the carvers depicted. When researchers do that comparison, they find something that lands in the territory between straightforward confirmation and genuine mystery. Some elements of the Dendera zodiac match the sky of around 50 years before the Common Era with a precision that is difficult to explain as coincidence. The positions of Mercury, Venus, Mars, Jupiter, and Saturn appear to record a specific date or narrow range of dates from that period. This is what Colville and her colleagues have argued, and the mathematical fit is real. Other elements of the composition are harder to explain by the sky of that single date. The decan positions, the arrangement of certain figures around the outer ring of the stone, have led other researchers to suggest that the composition is not a snapshot of a single night or season, but a synthesis of observations made across a much longer span of time. Perhaps a schematic summary of Egyptian astronomical knowledge as it had accumulated over many centuries. Both readings may be partially correct. The Dendera zodiac may be a document that operates on more than one timescale simultaneously, recording specific planetary positions from the late Ptolemaic period while also preserving, in its deeper structure, a framework of stellar observation that stretches back through the dynasties. If that is true, then what looks like a single image is actually a layered document. Recent data on the surface, much older data beneath. The way a river deposit contains sediment from many different floods, laid down over many different seasons, compressed into a single readable cross-section. The argument remains open. The scholars have not agreed. Outside the museum, Paris moves through its ordinary night. Traffic and voices and the particular hum of a city that has been continuously inhabited for centuries. Inside the room where the zodiac hangs, it is quieter. A few visitors move past in the daytime. Most of them do not stop. The stone does not mind. It has been waiting since before Paris was a city. It can wait a little longer. What it tells us, even in the absence of final resolution, is something worth carrying into the rest of this story. The people who made it were not starting from nothing. They were the inheritors of a tradition of watching the sky that stretched back, in some form, for longer than the building they worked in had existed. They carved into stone not just what they saw, but what they had been taught, what their teachers had been taught, what generations of watchers before them had recorded and passed on and slowly refined. That picture was the product of time, of patience, of a kind of institutional memory that kept accumulating knowledge across dynasties and invasions and the ordinary catastrophes of history, adding to what was known, preserving what had been observed, and eventually encoding it all into a piece of sandstone that a French engineer would cut from a ceiling and ship to Paris in 1820. The stone is in its room. The room is quiet tonight, and the sky it depicts is still up there, in positions slightly different from where the carvers placed them, shifted by the slow wobble of the earth that no single lifetime is long enough to observe on its own. That wobble is where we are going next. Chapter 2. The Slow Wobble. There is a fact about the Earth that takes a moment to absorb properly. The planet you are lying on right now is not entirely stable. Not in the way the word stable suggests when you use it about something you trust to hold your weight. The ground is moving. Not just in the obvious sense. Not just in the sense that the planet is spinning and orbiting and hurtling through the galaxy at speeds that become meaningless when you try to hold them in your mind. It is moving in another way. A slower way. A way that operates on a timescale so large that no single human life and no single human civilization is long enough to watch it complete a full cycle. Let that thought settle for a moment. The axis of the Earth is tilted. You probably learned this at some point. It is the reason there are seasons. The reason the northern hemisphere leans toward the sun in June and away from it in December. The reason the length of the day changes across the year in ways that ancient peoples tracked with extraordinary care. The tilt is real, and it has shaped the entire history of agriculture and civilization in ways that are difficult to fully account for. But the tilt is not fixed. The axis wobbles. Slowly. The way a spinning top wobbles when it begins to lose momentum, tracing a wide circle in the air above the table. The Earth's axis traces the same kind of circle, pointing at different parts of the sky as the centuries pass, completing one full wobble approximately every 25,772 years. This wobble has a name. It is called the precession of the equinoxes. Picture a single candle burning in a dark room. The flame is still. The shadows it throws on the walls are steady. Now imagine that the candle is very slowly tilting. So slowly that you cannot see the movement in any single moment. But if you came back to the room after a century, the shadows would have shifted to different parts of the walls. The North Star is the candle. The shadows are the positions of every other star in the sky. And the tilt is the precession. Polaris. The star that navigators have used for centuries as a fixed reference point in the night sky is not permanently the North Star. It is the North Star right now. In this particular century, because the Earth's axis happens to be pointing approximately in its direction. In the year 3000, before the Common Era, when the pyramids of Giza were being planned and built, the pole star was not Polaris. It was a different star entirely. A star in the constellation Draco called Thuban, a star that most people living today would not recognize by name. And in the year 14,000 of the Common Era, the pole star will be Vega, one of the brightest stars in the summer sky. The sky changes. Not quickly. Not in ways that any single person or any single generation would notice from casual observation, but it changes. Over centuries, the positions of the stars relative to the cardinal directions shift. The points on the horizon where the sun rises at the solstices and equinoxes drift. The constellations that appear in the east just before dawn in a particular season are different from the ones that appeared there 1,000 years earlier. Outside tonight, somewhere, a clear sky is turning slowly overhead. The stars that are visible right now were not visible from this same latitude, at this same hour, of this same night, 1,000 years ago. Different stars stood where these ones stand. The sky is not a fixed backdrop. It is a slow river, carrying everything with it. So slowly that no single life is long enough to see the current. Now, hold that fact alongside another one. To notice this change, to recognize that the sky is slowly moving. You need something that no single human life can provide. You need continuity. You need observations made at the same place, at the same time of year, compared across a span of time long enough for the drift to become measurable. Not a lifetime, not even several lifetimes. A sustained effort, passed from teacher to student, to student, to student, accumulating small measurements across generations until the pattern becomes visible. Let that image settle too. Not a single genius working alone, but a chain of patient people, each one adding one small piece to a picture none of them would live to see completed. The Greek astronomer Hipparchus is credited with the formal discovery of precession in approximately 127 years before the Common Era. He achieved this by comparing his own stellar observations with records made by earlier Babylonian and Greek astronomers. Noticing that the positions of certain stars had shifted in ways that required explanation, his calculation of the rate of precession was not perfectly accurate by modern standards. But it was real. It was based on real data, accumulated over real time, by real people who had been watching the same sky from one generation to the next. What Hipparchus had was access to a record that stretched back further than his own lifetime, a record that someone had kept carefully, for reasons that may have had nothing to do with discovering precession and everything to do with the practical requirements of a civilization that needed to track the seasons, time, religious festivals, and predict the flooding of rivers. Imagine him for a moment, a scholar in a lamplit room, unrolling a papyrus that records observations made 1,000 years before his birth. He compares those observations with what he saw from his own rooftop last night. The stars have moved. Not by much, but enough. He writes down the difference and reaches for another scroll. That gap between the observations on his oldest scroll and the sky outside his window is the gap in which precession reveals itself. The night is quiet. Let that image rest there for a moment. The question that archaeoastronomers have been asking ever since is a deceptively simple one. How far back does the record go? Hipparchus worked in the 2nd century before the Common Era. The Babylonian observations he drew on reached back at least several centuries further. The Egyptian Deccan system encoded in the coffin texts of the Middle Kingdom reached back 2,000 years before the Common Era or earlier. The builders of Newgrange in Ireland oriented their tomb to the winter solstice sunrise around 3,200 years before the Common Era. The builders of Göbekli Tepe in Turkey raised their carved stone pillars around 9,500 years before the Common Era. Before agriculture, before pottery, before any written record anywhere on Earth. Each of these represents a point on a line, a point where we can say with reasonable confidence that someone was watching the sky systematically, carefully, with enough continuity to leave patterns that modern tools are only now helping us understand. And when you draw the line through those points and extend it backward, the question it raises is one that the evidence has not yet fully answered. Was anyone watching before that? Was the tradition of systematic sky watching older than any monument we have yet found? Was there knowledge accumulated in communities that left no stone and no tablet and no trace of any kind that our instruments can currently detect? We cannot say with certainty. What we can say is that the sky rewards patience in ways that become visible only across very long spans of time, and that the communities who built the monuments we are going to visit tonight had clearly been watching long enough to leave patterns that modern tools are only now helping us understand. The wobble of the Earth continues tonight, as it has continued every night for the 4.5 billion years the planet has existed. It does not hurry. It does not pause. It traces its vast, slow circle with a patience that makes every human institution, every dynasty, every civilization that has ever claimed permanence look brief and fragile by comparison. And somewhere in that slowness, in the barely perceptible drift of the stars across the generations, The ancient world left its deepest and most durable record. We are still learning to read it. Chapter 3. The Pyramid and the Wandering Pole. In the year 2000, a paper appeared in the journal Nature that changed the way scholars thought about one of the oldest questions in Egyptology. The question was simple. It had been asked almost as long as the pyramids had been studied by anyone who paused long enough to wonder about them. How did the ancient Egyptians achieve the extraordinary directional accuracy of the Great Pyramid of Giza? The Great Pyramid is oriented to true north, with an error of approximately 3/100ths of a degree. Sit with that number for a moment. 3/100ths of a degree is smaller than the apparent diameter of the Moon as seen from Earth. It is a margin of error that modern surveyors, working with laser equipment and satellite positioning, would not be embarrassed by. It is a margin of error that, in 2,500 years before the Common Era, without any of those tools, without GPS, without a magnetic compass, without any instrument that has been identified in the archaeological record, required a method of exceptional precision. Scholars had proposed various explanations over the years. Some suggested the Egyptians used the shadow of the sun, tracking its movement across a precisely leveled surface to establish a true east-west line. Others proposed the stars, identifying the celestial North Pole by observing the circular paths of circumpolar stars and bisecting those paths geometrically. Both methods are theoretically sound. Neither had been definitively proven. The paper published in Nature in 2000 was written by Kate Spence, an Egyptologist at Cambridge University. Picture her at her desk, surrounded by survey data from dozens of pyramids, working through a problem that had occupied Egyptologists for generations. She was not the first person to study this question. She was, arguably, the first person to notice something in the data that everyone else had overlooked. The Great Pyramid is not the only pyramid. There are dozens of them, built across a span of several centuries during the Old Kingdom period. And when you measure the directional errors of each one, you find something that should not be there if the errors were simply the result of imprecise workmanship. The errors are not random. They form a pattern. The pyramids built earlier than the Great Pyramid have errors that deviate in one direction. The pyramids built later have errors that deviate in the other direction. The Great Pyramid itself, built around 2,560 years before the Common Era, has the smallest error of all. It sits at the turning point of the pattern, the moment when the method was most accurate. Random errors scatter in all directions. These do not. They trend in one direction, and then reverse, which means something systematic was happening. Something that was accurate at one specific moment in time, and then drifted away from accuracy as the centuries passed. Spence's explanation was elegant. She proposed that the Egyptians established true north by observing two specific stars that circled the celestial North Pole. A star, called Kochab, in the constellation we call Ursa Minor, and a star called Mizar in the constellation we call Ursa Major. By watching for the moment when these two stars were perfectly aligned vertically, one directly above the other, the Egyptians could identify true north with great precision. At that specific moment, the line connecting the two stars passed through the celestial pole, and a plumb line held against that alignment pointed directly north. It is a beautiful method. It requires no instruments beyond a plumb line and a patient eye. It requires knowledge of which stars to watch and when. And it works with a precision that the Great Pyramid's orientation confirms. The key insight was what precession does to this method over time. Because precession moves the celestial pole across the sky. The alignment of Kochab and Mizar with the true pole was not constant across the centuries of pyramid building. In approximately 2,460 years before the Common Era, the alignment was perfect. The two stars and the pole formed an exact vertical line. And the north, determined by that alignment, was true north. But in the centuries before and after that date, the pole had drifted slightly away from the line connecting the two stars, introducing a small but measurable error into any survey that relied on the same alignment without adjustment. The direction of that error, and its magnitude, changed, predictably, as precession moved the pole, and when Spence calculated the errors that the drifting alignment would have produced in each century of the Old Kingdom, the pattern matched the pattern of errors actually observed in the pyramids. Think about what that moment of recognition must have felt like. Sitting at a desk in Cambridge, working through calculations that no one had thought to make in quite this way before, and watching a pattern in ancient data suddenly reveal its explanation. The pyramids had been standing for 4,500 years. The signature of the Earth's wobble had been written into them the entire time, and it had taken until the year 2000 for someone to read it. The Earth's wobble had written itself into the pyramids without the pyramid builders knowing it was doing so, and the signature it left was precise enough that a Cambridge Egyptologist could read it back out 45 centuries after the last stone was set. Spence's paper has been discussed and debated and refined since its publication. Other scholars have proposed slightly different stellar pairs or slightly different methods. The debate about the precise mechanism continues, but the core finding has held. The orientational errors of the Old Kingdom pyramids are not random. They are systematic. They contain information, and that information is consistent with the use of a stellar observation method that was affected, in predictable ways, by the slow wobble of the Earth's axis. It is important to be precise about what Spence's research establishes and what it does not. It establishes that the pyramid builders were using a stellar observation method sensitive enough to be affected by precession. It establishes that they maintained this method consistently across multiple generations of pyramid building, which implies an institutional tradition of astronomical observation that persisted across the Old Kingdom. It establishes that this tradition was precise enough to orient massive stone structures to within fractions of a degree. What it does not establish is a theoretical understanding of precession on the part of the pyramid builders. They did not need to know that the Earth's axis was wobbling in order to use the Kochab and Mizar alignment consistently. They needed only to have been using the same method, watching the same stars, trusting the same alignment, without realizing that the alignment was slowly drifting because no single generation of observers was alive long enough to detect the drift on their own. The drift happened anyway, and it left its mark in the stones. Outside, tonight, Kochab and Mizar are still up there, higher in the sky now than they were when the pyramids were being built. Their relationship to the pole shifted by 4,500 years of precession. If someone tried to use Spence's proposed method tonight, watching for the moment when Kochab sits directly above Mizar, the north they found would be slightly off. Not by much, but by the small, systematic, measurable amount that precession dictates. The pyramid builders did not know their method was drifting, but the drift is how we know now that they were using it. That is a remarkable kind of evidence. Not a text, not a diagram, not a description of the method written down by someone who wanted to preserve it. Just the accumulated errors of many buildings, laid out across the desert over several centuries, waiting for someone to notice that the errors were not random. Kate Spence noticed. And in noticing, she gave us a window into a tradition of sky watching that was already old when the first pyramid was being planned. Chapter 4. Temples Built for Light. There is a morning in Egypt, once a year, when something happens inside a cliff. The cliff is on the west bank of the Nile, in what is now southern Egypt, close to the border with Sudan, in a landscape so remote and so dry that the air itself seems to have been emptied of everything except heat and silence. The monument carved into that cliff face is called Abu Simbel. 4 colossal seated figures on the facade, each one approximately 20 meters tall. their faces carrying the particular expression of Egyptian royal sculpture that suggests not emotion but eternity. But the photographs rarely show what is inside. The inner sanctuary of Abu Simbel is at the end of a corridor approximately 60 meters long, carved into the living rock of the cliff. At the far end of that corridor, 4 seated statues occupy a small chamber. 3 of them represent gods. One of them represents the pharaoh Ramesses II, deified. Seated among the gods, he identified himself with the 4th statue, the one on the far left, represents the god Ptah, who is associated with darkness and the underworld. On 2 mornings each year, the light of the rising sun enters the temple. It travels the full 60 meters of the corridor. It reaches the inner chamber, and it illuminates 3 of the 4 statues in a shaft of light that lasts for approximately 20 minutes before the sun moves and the corridor returns to its ordinary darkness. The statue of Ptah remains in shadow. Every year, on those 2 mornings, the 3 statues are lit and the 4th is dark. This is not accidental. The precision required to orient a corridor carved into solid rock so that the sunrise on a specific calendar date illuminates 3 specific statues 60 meters away is not achieved by chance. Someone understood, with considerable precision, where the sun would rise on the relevant morning and at what angle its light would enter the cliff. Someone calculated this before the first chisel touched the rock. The 2 days on which the illumination occurs fall approximately 60 days before and after the winter solstice. They have been connected by some researchers to dates of personal significance to Ramesses, possibly his birthday and the anniversary of his coronation, though this identification remains uncertain and should be understood as such. What is not uncertain is the intent. The corridor was built to do exactly what it does. When Abu Simbel was relocated in the 1960s to save it from the rising waters of Lake Nasser, the engineers who moved it discovered that the relocation had shifted the solar alignment by exactly 1 day. The light now arrives on the 21st of February and the 21st of October rather than the 22nd. The error introduced by moving an entire cliff face 65 meters is a single day across a 60-meter corridor carved into rock 3,300 years ago. That error is a measure of what the original builders achieved. Let that number sit for a moment. 3,300 years. The people who calculated the angle were not archaeologists reconstructing a lost tradition. They were practitioners of a living one, working within a framework of solar observation that had been accumulating precision for centuries before Ramesses ever commissioned his monument. Now think about the engineers who moved the temple in the 1960s. They had modern survey equipment, precise measurements, every technical advantage that 3,000 years of accumulated knowledge could provide. And when they set the temple down in its new position, they were off by 1 day. The builders of the original, working with plumb lines and patient eyes and the accumulated knowledge of a tradition that stretched back through the dynasties, had done something that the engineers of the modern world could barely match even with all their instruments. That is not a small thing. Abu Simbel is the clearest case in Egypt, the one where astronomical intent is most legible and least subject to interpretive dispute. But it is not an isolated case. Juan Antonio Belmonte, of the Instituto de Astrofísica de Canarias, has devoted much of his career to the systematic study of astronomical orientations in Egyptian temples, applying survey instruments and statistical methods to a problem that had previously been addressed with varying degrees of rigor. His approach begins with measurement rather than theory. He measures the orientations of a large sample of temples, records the results, and then asks what the distribution of those orientations tells us about the astronomical priorities of the people who built them. What the measurements show, across a substantial sample of Egyptian temples, is that there is genuine astronomical intent in the orientations of many of these buildings. The axes cluster around directions corresponding to the rising and setting points of the sun at the solstices and equinoxes, the rising points of specific bright stars, and in some cases, the rising point of the moon at particular moments in its cycle The clustering is real in a statistical sense. The orientations are not random. But Belmonte is careful about what the clustering means and what it does not mean. Each temple is a separate case. The astronomical target of one temple cannot be assumed to be the target of another. Egyptian temple building spanned 3,000 years and encompassed dozens of different cult centers with different theological traditions, different patron deities, and different ritual requirements. Any attempt to impose a single explanatory framework on all of them at once is going to produce oversimplification. Giulio Magli of the Politecnico di Milano has argued that the main axis of the Great Temple complex at Karnak was oriented toward the setting sun on the day of the summer solstice, creating a corridor of light along the temple's main axis at the moment of the year that held the deepest cosmological significance in the theology of the sun god Amun-Ra. The orientation has been measured, and the solstice alignment is real. Whether it was the primary intention of the original builders, or one consideration among several that shaped the axis, is a question the evidence has not yet fully resolved. Here is where intellectual honesty requires pausing. Popular accounts of Egyptian temple astronomy sometimes present the alignments as fully proven, as confirmed facts about ancient intention that require no further qualification. The reality is more nuanced. The alignments are real in the sense that the measurements confirm them. The intentions they reflect are inferred from the alignments, not directly documented. The inference is often compelling. It is still an inference. What can be said with confidence is this: the builders of Egyptian temples were sophisticated observers of the sky. They oriented their buildings with precision that required careful measurement and sustained tradition. They understood the annual cycle of the sun with sufficient precision to capture its light at specific moments and direct it to specific locations within their sanctuaries. And they were doing this not as a one-time achievement, but as an ongoing practice, generation after generation, in a tradition that stretched across dynasties and disruptions and 3,000 years of continuous civilization. There is something else worth noting, something that measurements and statistics can sometimes obscure. These buildings were not astronomical instruments in the way that a telescope is an astronomical instrument. They were houses for gods. The light that entered them on the relevant mornings did not serve a scientific purpose. It served a theological one. It connected the temple, at the most significant moments of the year, to the cosmic forces that the temple existed to honor. The precision of the alignment was in service of that connection. And in a desert where the light arrives without apology, where the angle of the sun on a specific morning can determine whether a sanctuary is illuminated or dark, the invitation was one that required extraordinary precision to extend correctly. The craftsman who carved Abu Simbel got the angle right. 3,300 years later, on the morning of the 21st of February, the sun still accepts the invitation. One day late, because of the relocation, but still there, still filling the corridor with light, still leaving the statue of Ptah in its intended darkness. Chapter 5. The Pillar of Foxes. In the hills of southeastern Turkey, on a limestone ridge where the wind comes in from the Syrian plain and the nights are very cold and very clear, there is a site that has been quietly revising the story of human civilization for 30 years. Not revising it in the dramatic way that popular accounts sometimes suggest. Not revealing a lost advanced civilization or a hidden chapter of history that changes everything we thought we knew. Revising it in the more patient and more permanent way that genuine archaeological discoveries revise things. By presenting evidence that does not fit comfortably into the existing story and forcing the story to make room. The site is called Göbekli Tepe. The name means Potbelly Hill in Turkish. It does not sound significant. For most of the 20th century, it was not recognized as significant. A mound on a hilltop in a region full of mounds. Noted and passed over by earlier surveys. In 1994, a German archaeologist named Klaus Schmidt decided to look more carefully. Schmidt had spent years working at prehistoric sites across Turkey. He had a practiced eye for the difference between natural rock formations and worked stone, between the accidental accumulations of time and the deliberate constructions of human hands. When he looked at the mound at Göbekli Tepe, something in the surface exposures made him stop. He began to excavate. What he found beneath the surface of that hill was not a medieval cemetery or a Byzantine settlement or anything that the landscape of southeastern Turkey would have led an experienced archaeologist to expect. What he found were massive stone enclosures, circular and rectangular, built from T-shaped limestone pillars up to 6 meters tall and weighing between 7 and 10 tons each. Schmidt would spend the rest of his working life at Göbekli Tepe. He died in 2014, 20 years after that first careful look at the hillside, with the site still yielding discoveries that surprised him. In interviews conducted in his later years, he described the experience of excavating Göbekli Tepe as one of continuous revision, a site that kept refusing to conform to any existing framework, and that seemed, no matter how much was uncovered, to have more waiting beneath the surface. The pillars he uncovered were carved with images of animals, rendered with a naturalism and confidence that spoke of a tradition of stone carving that had been developing for a long time before it produced this. Snakes coiling down the surfaces, foxes with their distinctive pointed ears, vultures spreading their wings across the stone, boars, cranes, scorpion, spiders, arranged in compositions that do not look like casual decoration. They look like statements, like images that were chosen for reasons that matter deeply to the people who made them. Some of the pillars have arms, human arms, carved in relief on the sides of the T-shaped shafts, with hands and fingers that make the pillars look less like architectural elements and more like representations of beings, ancestors, perhaps, or something for which the people who carved them had a name that has not survived. The site dates to approximately 9,500 years before the Common Era, the pre-pottery Neolithic, a period when the people of this region were, according to the standard picture, hunter-gatherers not yet settled into the villages that agriculture would eventually make possible. Hunter-gatherers do not build temples. That was the assumption, and this hill broke it. The logistics of the site require reconsidering what these people were capable of. The limestone pillars were quarried at a source about 100 meters from the enclosures and moved to their current positions without metal tools, without the wheel, without draft animals. The largest unfinished pillar, still lying in the quarry, is approximately 7 meters long and would have weighed around 50 tons. Moving the finished pillars required coordinated group labor of a scale and duration that implies social organization considerably more sophisticated than the mobile bands that most models of this period describe. Someone organized this work. Someone had the authority, or the persuasion, or the social power to direct large numbers of people to do difficult physical labor in a coordinated way over an extended period. What form that authority took, we cannot say. The site has yielded no obvious markers of individual wealth or status. Nothing that maps cleanly onto the political structures of later civilizations. But the work got done. And then, at some point, the enclosures were deliberately buried, not abandoned and left to ruin, filled in, methodically, with a mixture of flint chips and animal bones and soil, in a process that appears to have been intentional rather than accidental. The filling preserved the structures remarkably well, and it raises a question that has occupied researchers ever since. Why would you bury something you had put that much effort into building? The honest answer is that we do not know. The people who made the decision left no written explanation. Theories have been proposed that the burying was a ritual act, a form of closing or consecrating the space, that each enclosure represented a specific period of use, after which it was deliberately closed and a new one opened nearby, that the burying was protective, intended to preserve the enclosures against some anticipated disruption. None of these explanations has been confirmed. All of them remain possible. Let the cold air in from the Syrian plain for a moment. Let the stars come out over the limestone ridge. Let the questions sit without an answer. The way the best questions do. Now, here is where the astronomical argument enters. And here is where the story requires the most careful handling. Because this is the territory where legitimate research and overreach have been most thoroughly mixed. And the mixing has done real damage to the ability of non-specialists to evaluate what the evidence actually shows. In 2017, two researchers at the University of Edinburgh, Martin Sweatman and Dimitrios Tsikritsis, published a paper arguing that the carvings on one specific pillar at Göbekli Tepe, a pillar known as Pillar 43, may represent a star map recording a specific astronomical configuration at a date around 10,950 years before the Common Era. The pillar they focused on is one of the most elaborately carved at the site. A large vulture with a rounded object balanced on one wing. A scorpion below it. Other animals arranged across the surface. Sweatman and Tsikritsis argued that these figures could be read as representations of constellations. The vulture corresponding to Sagittarius and the scorpion to Scorpius, with the rounded object representing the sun at a specific position in the sky. If that identification were correct, precession calculations would place the depicted configuration at a specific historical date. The paper attracted considerable attention. The critical response from the broader archaeological and archaeoastronomical community has been substantial and deserves to be taken seriously. Several researchers pointed out that the identification of the carved figures with specific constellations is not straightforward. The connection between the animal figures and the star groupings of the modern zodiac requires a series of assumptions that are not independently supported. We do not know what constellation figures, if any, the builders of Göbekli Tepe recognized. We do not know how they grouped the stars or whether they connected star positions to the animals they carved on stone. The constellation framework that Sweatman and Tsikritsis used is inherited from Babylonian and Greek astronomy, a tradition that did not exist in the form they assumed at the time Göbekli Tepe was built. These are serious criticisms. They do not mean the paper was worthless. It raised a question worth asking and applied a method that produced a specific and testable claim. But the criticisms mean that the paper's conclusions should be held lightly rather than treated as established findings. The genuine question that Göbekli Tepe raises about the sky, the one that survives all the controversy about specific interpretations, is more interesting and more durable than any single paper's conclusions. The orientation evidence at the site, studied with appropriate statistical care, suggests that the builders may have been paying deliberate attention to specific astronomical directions when they placed their enclosures and their central pillars. The word may is doing real work in that sentence. The evidence is suggestive. Each new enclosure uncovered adds to the picture. But the picture has not yet reached the clarity that would allow confident claims about specific astronomical targets. What is not in dispute is the scale of what remains to be learned. Current estimates suggest that no more than 5 to 10% of Göbekli Tepe has been excavated. Geophysical surveys have identified at least 15 additional enclosures still buried underground. The site was occupied and modified over a span of roughly 1,500 years. The material it contains represents 1,500 years of cultural activity by communities whose relationship to the sky we are only beginning to understand. Picture it at night, the way Schmidt must have pictured it in those early years of excavation. Lying awake in the field station, wondering what the next morning's work would reveal. The cold air from the Syrian plain, the stars above, a landscape that looked, from a distance, like nothing in particular. Beneath the surface, the carved pillars waiting in their deliberate darkness, the foxes and the vultures facing directions that someone, 11,000 years ago, chose with intention, the enclosures filled and buried by the same hands that built them. for reasons that made complete sense at the time, and that we may eventually understand if we are patient enough and careful enough and humble enough about what we do not yet know. The hill is still giving up its secrets. One brushstroke at a time. Schmidt spent 20 years at this hill. He did not live to see most of what it still contains. The researchers who came after him will spend their careers here too. And the researchers who come after them. The site will outlast all of them. The way it has outlasted everything else, since the last stone was set and the last enclosure was filled, and the builders walked away into a world that has entirely ceased to exist. But the pillars are still here. And the foxes are still looking at something. Chapter 6. The Temptation of 10,500 BCE. There is a particular kind of argument that appears regularly in the literature of ancient mysteries. And it has a structure worth learning to recognize. Not because the people who make it are dishonest, but because the argument itself has a flaw built into its foundation that causes it to produce compelling results even when those results are not warranted by the evidence. The argument works like this. You take a significant ancient site. You measure its layout, the positions of its major structures, the directions its axes point, the spatial relationships between its component parts. You then ask whether that layout corresponds to the pattern of a particular constellation or group of constellations as seen from Earth. And you use precession to calculate backward through time, asking at what historical date the correspondence would have been most precise. When you find a date where the correspondence looks good, you propose that the builders were encoding that astronomical configuration into their architecture, and that the date you have calculated represents either the true date of construction or a moment of cosmological significance the builders were deliberately commemorating. The mathematics involved are real. The precession calculation is genuine. The software that performs it is reliable and available to anyone. The problem is what happens before the mathematics. In the step where you decide that the layout of the site corresponds to a particular constellation pattern. Constellations are human inventions. They are not objects in the sky. They are lines drawn between stars by cultures that needed to organize the overwhelming complexity of the night sky into a set of memorable figures. Different cultures drew different lines. The Babylonians drew one set. The Greeks inherited and modified it. The Chinese drew another set entirely. The Aboriginal Australians of some regions saw constellations not in the bright stars but in the dark patches between them. The spaces where the Milky Way thins and the sky deepens to black. When a modern researcher looks at an ancient site and asks whether its layout matches the pattern of a constellation, the constellation pattern they are almost always using is the one inherited from the Babylonian and Greek tradition. That tradition did not exist in anything like its current form before the first millennium, before the Common Era. Projecting it backward onto sites that predate it by thousands of years requires assuming that the builders were using the same constellation framework that much later cultures would develop. That assumption is not supported by independent evidence. And the results it produces need to be evaluated with that assumption clearly in view. Now, bring this to the case that has generated more popular attention than almost any other in archaeoastronomy over the past 30 years. Robert Bauval is a Belgian-born engineer and author who proposed, in a book published in 1994, that the three pyramids of Giza were laid out on the ground to mirror the pattern of the three belt stars of Orion. The visual correspondence is striking. The pyramids are not in a perfectly straight line. They have an offset, with the smallest of the three sitting slightly to one side. The three belt stars of Orion have a similar kind of offset. Bauval applied precession to ask when the belt stars of Orion would have been at a specific position in their precessional cycle, and arrived at a date of approximately 10,500 years before the Common Era. He proposed that this date was the cosmological anchor of the Giza complex, the moment in astronomical time that the pyramid builders were referencing in their layout. The proposal attracted enormous popular attention. It also attracted substantial scholarly criticism. Egyptologists pointed out that the three pyramids were not built simultaneously or as part of a single planned layout. They were built by three successive pharaohs across approximately a century, with each pharaoh choosing a location that had practical as well as ceremonial considerations. The spatial relationship between them was not the product of a single design decision made at a specific astronomical moment. Other researchers pointed out that the correspondence between the pyramids and the belt stars, while visually suggestive, is less precise than claimed when examined carefully. The relative sizes of the pyramids do not match the relative brightnesses of the belt stars. The orientation of the pyramid group does not match the orientation of the belt stars relative to the Milky Way as precisely as the published images suggested, and the date of 10,500 years before the Common Era corresponds to a period more than 8,000 years before the pyramids were actually built. No explanation grounded in the archaeological record has accounted for that gap in a way that the scholarly community has found convincing. There is also a deeper methodological problem. When you ask a precession calculator to find the date at which a group of three objects arranged in a particular spatial relationship best matches a group of three stars in a similar relationship, you will find a date. The question is whether the match at that date is genuinely better than matches at other dates, and whether it is better than matches you would find if you compared the same site layout to entirely different star groupings. Critics have argued that the methodology used in the Orion correlation theory does not adequately test these alternatives. If you try enough combinations, the mathematics will eventually hand you a date that looks meaningful. Wobble subsequently collaborated with the writer Graham Hancock to extend the argument to a wider range of ancient sites. Their work proposed that the temple complex at Angkor Wat in Cambodia was laid out to mirror a constellation as it appeared at approximately the same date of 10,500 years before the Common Era. The Angkor Wat correlation was examined by researchers familiar with the site and found to depend on selective use of which temples to include in the comparison and which to exclude. When the full complex is considered, the correspondence is considerably less compelling than the published images suggested. The scholarly literature has not accepted the hypothesis of a lost civilization at 10,500 years before the Common Era on the basis of these astronomical correlations. The absence of any direct archaeological evidence for such a civilization, combined with the methodological concerns about the correlation method, has kept the hypothesis outside the mainstream of professional scholarship. Now here is the thing worth holding as this chapter closes, because there is a real question underneath the dramatic one, and it deserves to be separated from the methodology that has sometimes obscured it. The question of whether ancient builders were encoding astronomical knowledge into their architecture, and whether that knowledge might be older than the buildings themselves, is a legitimate and genuinely important question. It is the same question that Kate Spence's research addresses, and that Belmonte's surveys of Egyptian temples address, and that the orientation studies at Göbekli Tepe address. The difference is in the standard of evidence. When Spence demonstrates that the directional errors of the Old Kingdom pyramids form a systematic pattern consistent with a specific stellar observation method affected by precession, she is working with measurements, with statistics, with a falsifiable prediction that either matches or does not match the data. The match is there. The argument is grounded. When the Orion correlation theory proposes that the Giza layout mirrors the belt stars at a date 8,000 years before the pyramids were built, the argument requires a chain of assumptions that are not independently verifiable, and the methodology does not adequately test whether the apparent correspondence is better than chance. The distinction between those two kinds of argument is not pedantic. It is the difference between knowledge and speculation. Both are legitimate activities. History needs speculation to generate hypotheses worth testing, but speculation presented as established fact, repeated confidently enough that it begins to feel proven, does a particular kind of damage. It makes the real discoveries harder to appreciate, because the extraordinary has been diluted by the merely dramatic until a listener no longer knows where to direct genuine astonishment. The real discoveries are astonishing enough on their own. The Great Pyramid oriented to true north with an error of 3/100ths of a degree. The solstice light at Newgrange, traveling 19 meters to illuminate a carved chamber. The Venus cycle and the Dresden Codex accurate to within 2 hours over 5 centuries. These things do not need a lost civilization of 10,500 years before the Common Era to be extraordinary. They are extraordinary on their own terms. Produced by real people working within real traditions of careful and sustained observation. The temptation of the dramatic date is understandable. The desire to find a single explanation, a single civilization, a single moment that unlocks the mystery of ancient sophistication, is a human desire and not an ignoble one. The ancient world feels less overwhelming if you can place a name and a date on its deepest questions. But the actual story, the story of generations of patient watchers, building knowledge slowly across centuries and millennia, passing it forward in traditions that changed and grew, and sometimes were lost, and sometimes survived in ways nobody expected, is more interesting than any single lost civilization, because it is a story about something that actually happened, and the traces of it are still in the stones. Chapter 7. The Priests Who Memorized the Sky. There is a tradition in the study of ancient knowledge that tends to look for its objects in the obvious places. In libraries, in archives, in the physical remains of writing systems sophisticated enough to survive the processes of copying and translation and rediscovery that brought us Euclid and Archimedes and the astronomical tables of Ptolemy. The assumption embedded in that tendency is that knowledge which was not written down was not really preserved. That oral traditions are approximate, subject to the distortions of memory and the gaps of forgetting. Suitable perhaps for poetry and narrative, but not for the precise numerical information that astronomy requires. That assumption has been significantly challenged in recent decades by research suggesting it underestimates both the sophistication of oral knowledge systems and the lengths of time over which they can preserve information with remarkable fidelity. Picture a room in ancient Babylon. Lamplight. The smell of clay. A scholar unrolling a tablet that records observations made 1,000 years before his birth, comparing what is written there with what he saw from his rooftop last night. The stars have moved. Not by much, but enough. He writes down the difference. He reaches for another tablet. That scholar is working with what we now call the Mul-Apin tablets. The name means plow star in the ancient Babylonian language, referring to the star grouping that appears at the beginning of the text. The tablets themselves date to approximately 1,100 years before the Common Era. But the astronomical content they contain is considerably older. The Mul-Apin tablets are a compendium, a compilation of earlier astronomical knowledge organized into a systematic reference work. They describe the paths of the sun, moon, and planets across the sky. They list the dates on which specific stars rise and set. They provide a calendar of astronomical events tied to the agricultural and religious year. They include rules for predicting eclipses and for keeping the lunar calendar synchronized with the solar year. When researchers analyzed the stellar rising and setting dates listed in the tablets and asked at what historical period those dates would have been accurate, the answer pointed to a period approximately between 2,300 and 1,800 years before the Common Era. Roughly 1,000 years before the tablets were written down. 1,000 years of observations, preserved with sufficient accuracy to be incorporated into a reference work produced a millennium later and to retain enough precision that modern astronomers can date them. That is not casual preservation. That is institutional memory operating over a timescale that challenges ordinary assumptions about what early written and oral traditions can achieve. Let that settle for a moment. Outside, the night is the same night it always is. The same stars that the Babylonian scholar watched from his rooftop are up there now, shifted slightly by the centuries of precession. but recognizable. The same patterns that someone, 3,000 years ago, thought worth recording on clay, worth preserving, worth passing forward into a future they could not see. Now, the night air shifts. The scene changes. We move east and forward in time. The Vedic tradition of ancient India offers a different and in some ways more striking case. The Vedanga Jyotisha is an ancient Indian text concerned with the timing of religious rituals. It belongs to a class of supplementary texts attached to the Vedas, the oldest layer of Indian religious literature. Its astronomical content has been analyzed by researchers trying to establish when the observations it encodes were made. The text describes the positions of the sun and moon at the solstices and equinoxes in terms of the nakshatra system, a division of the sky into 27 or 28 segments corresponding to the daily motion of the moon. When researchers used precession to calculate backward and ask when the solar and lunar positions described in the text would have been accurate, some scholars have argued that at least portions of the observational content may reach back to the second millennium before the Common Era, or possibly earlier. It is important to say clearly that the dating of the Vedanga Jyotisha is one of the most contested questions in the study of ancient Indian astronomy. Different researchers using different methods have proposed dates ranging across nearly 2,000 years. This is an active area of genuine scholarly disagreement, not a settled question, and any specific date should be understood as one position in an unresolved debate rather than an established conclusion. What is not contested is that the text preserves astronomical observations accumulated across a long period of careful sky watching, maintained within a tradition of transmission that treated precision as a serious obligation. The Vedic tradition was primarily oral. The Vedas themselves were maintained for centuries in memorized form before being committed to writing. The preservation method was not casual. Students underwent years of rigorous training under teachers who enforced exact memorization, including not just the words, but the precise phonetic realization of every syllable. With a redundancy system in which the texts were memorized in multiple recombinations to guard against corruption, picture a young student in the early morning, somewhere in ancient India, repeating the words of his teacher, the same words his teacher repeated to his teacher, each syllable held to an exact standard, the sky outside carrying the same patterns that the original observers watched, shifted by the centuries of precession but still turning in its slow, reliable circle. The student does not fully understand everything he is memorizing. He does not need to. His job is to carry it forward intact, so that someone who comes after him will have what they need. That is the structure of knowledge transmission in a world without printing, without digital storage, without any medium more durable than trained human memory, and sometimes across spans of time that challenge every assumption about what oral traditions can hold. The knowledge arrives. The Maya tradition offers yet another kind of evidence, and this one is the most precisely documented. The Dresden Codex is one of 3 surviving pre-Columbian Maya books, written on folded bark paper and dating to approximately the 11th or 12th century of the Common Era, though the content it preserves is considerably older. Among other things, it contains a table of Venus appearances that tracks the cycles of the planet with a precision that has consistently astonished modern astronomers. Venus has a synodic cycle, the time it takes to return to the same position relative to the Sun as seen from Earth, of approximately 583.92 days. The Venus table in the Dresden Codex tracks the planet's cycles of visibility with an accumulated error of approximately 2 hours over a period of 5 centuries of observation. 2 hours over 5 centuries. That is not an approximation. That is a measurement. The product of sustained, systematic observation, maintained with a precision that required not individual genius, but institutional continuity. A tradition of watchers who recorded what they saw, compared it to what earlier watchers had recorded, and refined their calculations across generations. The Venus table also contains correction factors, adjustments, built into the calendar to compensate for the accumulated drift between the ideal cycle and the actual observed positions of the planet. These corrections are evidence of something beyond observation. They are evidence of meta-knowledge, the recognition that the simple cycle is not perfectly regular and that a useful predictive tool needs to account for that irregularity. The people who built the Venus table were not just recording what they saw. They were building a model of what they would see, testing it against observation, and refining it when the prediction diverged from reality. That is the structure of scientific inquiry applied to the sky from a position that had no telescope, no mechanical clock, no calculating device beyond the human brain, trained across years of careful apprenticeship. Now there is a scholarly framework that attempts to explain how astronomical knowledge could be preserved not just in written texts, but in the mythologies and oral traditions of cultures that had no writing at all. In 1969, the historian of science Giorgio de Santillana and the mythographer Hertha von Deschend published a book called Hamlet's Mill. Their central argument was that the mythologies of ancient cultures around the world contain encoded astronomical information. Specifically, information about the precession of the equinoxes, preserved in the symbolic structures of myths about the end of ages, the rotation of a cosmic mill, the destruction and rebuilding of the world. The argument of Hamlet's Mill has had a complicated reception. It was widely read and genuinely influential. It was also criticized by professional mythographers and astronomers who found its methodology insufficiently rigorous and its identifications of astronomical content in myths too dependent on interpretation. The criticism is fair and should be acknowledged clearly. The specific claims about a single connected ancient tradition of precession knowledge stretching across all cultures are not supported by the evidence to the standard that would be required to accept them as established fact. But the underlying question the book raises has not gone away. And in the decades since its publication, researchers working with more rigorous methods have found evidence that supports a more modest and more defensible version of the core claim. The modest version is this: oral traditions are capable of preserving precise empirical information across much longer periods than was previously assumed. And the night sky, with its regular cycles and its slow precessional drift, is exactly the domain in which such preservation is most likely to occur and most useful to maintain. Because the sky is useful, it tells you when to plant and when to harvest. It tells you when the floods will come and when they will recede. It tells you how to navigate across open water without landmarks. It tells you when to hold your religious festivals. A culture that depends on the sky for all of these purposes has strong incentives to maintain precise knowledge of it, and strong incentives to develop methods of transmission that preserve that precision across the generations of inevitable individual forgetting. The priests who memorized the sky were not performing an act of cultural nostalgia. They were maintaining infrastructure. They were keeping a system running that their community depended on in the most practical ways. The ways that determined whether the harvest was good and whether the boats that went out over the horizon could find their way back. The knowledge they held was not mystical in the way that later romanticization has made it seem. It was technical. It was precise. It was the product of centuries of accumulated observation, maintained in traditions of training and transmission that treated astronomical knowledge with the same seriousness we give to any form of expertise a community depends on for its survival. What is extraordinary is not that they had this knowledge. What is extraordinary is how much of it survived. In the Venus table of the Dresden Codex, in the deacon lists of the Egyptian coffin texts, in the Mulapin tablets that preserve observations 1,000 years older than the clay they are written on, in the architectural orientations of temples whose builders knew, with precision that still surprises us, where the sun would rise on the morning that mattered most. The priests who memorized the sky are gone. Their names are not recorded. Their faces are not preserved. The schools where they trained exist now only as foundations in the archaeological record, if they exist at all, but the sky they memorized is still there. And we have learned, slowly and with great effort, to read some of what they left in it. Chapter 8. The Atlantic Stones. There is a field in Ireland that most people drive past without stopping. It sits in the Boyne Valley, about 50 kilometers north of Dublin. In a landscape of low green hills and slow rivers, and the particular quality of Irish light that changes every few minutes, as clouds move across a sky that cannot quite decide what it wants to be. The field has been farmed for centuries. The hedgerows are old. The soil is dark and deep, and has been turned so many times that its surface holds no obvious sign of what lies beneath it. But beneath it, and above it, and built into the hill that rises at the center of the field, there is something that has been standing for longer than the pyramids of Giza, longer than Stonehenge, longer than any structure in the Western world that most people have ever heard of. It is called Newgrange, and on the mornings around the winter solstice, it does something that no amount of description fully prepares you for. A narrow shaft of light enters a small opening above the main doorway of the mound. The opening is called the roof box, a deliberate architectural feature whose function puzzled archaeologists for years after the site was first scientifically excavated in the 1960s. The shaft of light travels down a 19-meter passage of carefully fitted stone, around two slight bends that do not interrupt its path, and enters the central chamber at the heart of the mound. For approximately 17 minutes, the chamber is illuminated. Then the sun moves and the light withdraws, and the chamber returns to the darkness it holds for the rest of the year. This illumination is most precise on the morning of the winter solstice itself, with the effect visible for a few days on either side, as the sun's rising point moves gradually along the horizon. Newgrange was built approximately 5,200 years ago, around 3,200 years before the Common Era. The people who built it left no writing. They left no record of why they built it, or what the solstice illumination meant to them, or what rituals, if any, they performed in the chamber on the mornings when the light arrived. What they left is the thing itself. And the thing itself is evidence of something that requires no interpretation to appreciate. The builders understood the solar year with sufficient precision to design and construct a stone passage that captures the sunrise around a single specific point in the calendar and directs its light to a specific location 60 meters away. They understood how to work stone with sufficient accuracy to execute that understanding at a scale that has maintained its function for 5,000 years. The archaeologist Michael O'Kelly conducted the primary excavation of Newgrange in the 1960s and 1970s. He was a careful scholar, methodical in his documentation, cautious in his interpretations. He initially assumed that the roof box was a decorative feature. It was only after he noticed the alignment of the passage with the solstice sunrise direction that he began to consider its astronomical function. He spent several years carefully measuring and remeasuring the alignment before he was confident enough to publish his interpretation. He did not simply trust what the geometry told him. He waited for the light. The first time O'Kelly witnessed the solstice illumination himself, standing alone in the chamber in the cold dark of a December morning, the experience affected him in a way that his published writing registers with a precision unusual in the archaeological literature. The light was not approximate. It did not graze the chamber or partially illuminate one wall. It entered fully, filling the inner chamber in a shaft that made every detail of the carvings on the back wall clearly visible for those 17 minutes. He had spent years knowing intellectually that the alignment was there. Standing in the light was something else entirely. The carvings on the back wall of the inner chamber are among the most elaborate examples of Neolithic art in Western Europe. Triply spirals, lozenge patterns, concentric arcs carved into the stone over a period of sustained effort that must have occupied skilled craftspeople for years. They were placed at the exact location where the solstice light arrives. The carvers knew the light would reach this wall. They decorated accordingly. Whatever the spirals meant to the people who made them, they were made for the light. Newgrange is not alone. It is part of a complex of passage tombs in the Boyne Valley that includes two other large mounds, Noath and Douth, each with its own astronomical alignment. Noath has two passages, one oriented toward the spring equinox sunrise and one toward the autumn equinox sunset. Douth has a passage aligned to the winter solstice sunset. The three mounds together suggest a community that was systematically mapping the turning points of the solar year into stone, marking each major astronomical threshold with a monument whose scale required decades of construction. The Boyne Valley complex is one node in a much larger phenomenon. The tradition of megalithic construction produced thousands of structures across a geographical range stretching from Scandinavia to the Mediterranean, from Ireland to the Black Sea. Over a period of roughly 2,000 years, during the 4th and 3rd millennia before the Common Era. Not all of these structures have documented astronomical alignments. Many have been damaged or destroyed, to the point where their original orientations cannot be reliably measured. The literature on megalithic astronomy contains a proportion of overclaiming that has made careful researchers appropriately cautious about the field as a whole. But the careful researchers are there, and their work is worth attending to. Clive Ruggles, who holds the UNESCO chair in archaeoastronomy, has devoted his career to the systematic study of astronomical alignments in prehistoric monuments, applying rigorous statistical methods to a problem that had previously been addressed with varying degrees of care. His analysis of Scottish megalithic monuments found that certain classes, particularly the recumbent stone circles of northeast Scotland, show a statistically significant tendency to align with the moon at specific points in its cycle. The moon has a more complex apparent motion than the sun. Its rising and setting points shift across a range considerably wider than the sun's, and the full range of that shift completes a cycle approximately every 18.6 years. The lunar standstills, the moments at the extremes of the moon's range, appear to have been astronomically significant to the builders of certain megalithic monuments. Ruggles established that this tendency is real in a statistical sense, not a pattern, projected onto random orientations by a researcher looking for patterns. The monuments were built with orientation as a deliberate criterion. Stonehenge is the monument most people think of when they think of megalithic astronomy, and it deserves its reputation. Though the reality is more interesting and more complicated than the simplified version that has circulated in popular culture for generations. Stonehenge was not built all at once. It grew across approximately 1,500 years, from roughly 3000 BCE to approximately 1500 BCE, with the most dramatic phase, the erection of the large sarsen stone circle and the trilithons, dating to approximately 2500 BCE. Different phases had different forms and possibly different astronomical orientations and different functions. The alignment most discussed is the orientation of the main axis toward the summer solstice sunrise and the winter solstice sunset. This alignment has been measured and confirmed by multiple independent researchers. Ruggles has argued that the monument's significance may have been primarily connected to the winter solstice sunset rather than the summer solstice sunrise, toward which the most elaborate architectural feature, the Great Trilithon, faces. Large quantities of animal bones found in the surrounding landscape suggest major feasting events at the midwinter period. The winter solstice, the shortest day, the turning point, after which the days begin to lengthen, again, appears to have held deep significance for the communities that built and used Stonehenge across its long history. The rows of standing stones at Carnac in the Brittany region of northwestern France present a different kind of monument, one whose astronomical interpretation has been more contested. Carnac is a landscape of extraordinary density. Thousands of standing stones, arranged in rows, stretching for kilometers across the low Breton hills. interspersed with circular enclosures and isolated single megaliths. Individual rows do appear to have orientations consistent with solar or lunar events. Whether those orientations represent deliberate astronomical targeting or a broader cultural tendency to build with generally favorable astronomical orientations is a question the data alone cannot resolve. What is not in doubt is that the people who erected the Karnak monuments were working within the same broad tradition of sky awareness that produced Newgrange and Stonehenge. The Atlantic coastline of Europe was, during the 4th and 3rd millennia before the Common Era, a world of considerable cultural connectivity. Maritime communities along the coasts of Portugal, Brittany, Ireland, Britain, and Scandinavia shared architectural traditions, burial practices, and material culture in ways visible in the similarities between their monuments, despite the distances separating them. The shared tradition of astronomical monument building is one of the most striking of these similarities. Communities separated by hundreds of kilometers of ocean were during the same centuries, building monuments oriented to the same astronomical events. The same turning points of the solar year encoded in stone from the Atlantic coast of Portugal to the islands of Orkney. These monuments were built to face specific directions. Those directions correspond to astronomically significant events. The precision required to achieve those correspondences exceeded what casual observation could produce. It required sustained, multi-generational attention to the sky, maintained within a tradition that treated that attention as important enough to embed its results in structures designed to outlast everything else their builders created. They lasted. The solstice light still enters the roof box at Newgrange on the mornings around the winter solstice. It travels the same 19 meters it has traveled for 5,200 years. It illuminates the same carvings on the same back wall of the same chamber that O'Kelly stood in. Alone, on a cold December morning more than 50 years ago, watching the light arrive and understanding, for the first time in his own body, what the builders had intended. Whatever it meant to the people who built it, it still does what they built it to do. 5,000 years later, on cold December mornings, in Ireland, the sun keeps the appointment they made for it. Chapter 9. Catastrophe, Memory, and the Sky. There is a question that sits at the edge of everything this story has been building toward, and it requires approaching with more care than almost any other question in this account. Not because the question is disreputable. It is not. It has been addressed by serious researchers using rigorous methods, and some of what they have found is genuinely remarkable. But the territory the question occupies has also been heavily traveled by people with less rigorous methods and more dramatic agendas. And the tracks they have left make careful walking harder. The question is this: how long can a community remember something? Not in the abstract sense. In the specific and concrete sense of a community that experiences a significant event, a catastrophe, a transformation of the landscape, a change in the sky, and then maintains the memory of that event across generations of telling and retelling, in stories and songs and ritual performances, without writing, without anything except the human voice passing the account from elder to student to student to student. How long can that chain hold? The traditional assumption in Western scholarship was that oral traditions degrade relatively quickly, that the span of reliable memory in an unwritten tradition is a matter of a few centuries at most, and that stories claiming to describe events from thousands of years ago should be treated as symbolic accounts of human experience rather than records of specific events. That assumption has been significantly revised by researchers working with indigenous oral traditions, particularly in Australia, where the combination of long cultural continuity, detailed ethnographic documentation, and datable geological and astronomical events has allowed researchers to test the reliability of oral memory over periods that would previously have been considered impossible. Duane Hamacher, a researcher at the University of Melbourne who works in the field of cultural astronomy, has documented cases in the oral traditions of Aboriginal Australian communities that appear to preserve accurate descriptions of specific astronomical and geological events that occurred thousands of years before the traditions were first recorded by European researchers. One of the most striking categories involves traditions describing landscape-forming events. Several Aboriginal traditions describe specific landscape features as the results of specific catastrophic occurrences. Fireballs falling from the sky. Land being transformed by forces from above. When Hamacher and his colleagues examined the geological record of the locations described in these traditions, they found evidence of impact events and other occurrences consistent with the descriptions, at dates that in some cases reach back several thousand years. Let that sit for a moment. Stories passed from grandmother to grandchild to grandchild to grandchild, across hundreds of generations, still carrying enough accurate information about a specific event at a specific place to be matched against the geological record thousands of years later. The match between the traditions and the geological record is not perfect in every case. Oral traditions are not recording devices. They are narratives, shaped by the needs of the communities that maintain them, changed by the process of telling in ways that are sometimes impossible to distinguish from the original content. But the correlations Hamacher has documented are not easily explained as coincidence. The traditions describe the right kind of event at the right location in terms consistent with what a witness of the original event would have experienced. This research has been published in peer-reviewed literature and received seriously by researchers in the relevant fields. It does not prove that all ancient traditions encode reliable memories of geological events. It demonstrates that some of them do. In specific cases where the tradition and the geological record can be independently compared. Now, bring this to the question of the sky and the sea. The flooding of coastal lands at the end of the last ice age was a real and significant event. Sea levels rose by approximately 120 meters over a period of roughly 10,000 years, drowning coastal territories that had been inhabited for generations and forcing populations inland. This is one of the most thoroughly documented events in the Earth science record. Patrick Nunn of the University of the Sunshine Coast and Nicholas Reed of the University of New England have documented Aboriginal Australian traditions that appear to describe specific locations now underwater, along coastlines submerged at specific periods following the end of the last ice age. The traditions describe these locations as places where ancestors lived, where significant events occurred, and where the sea has since advanced. When the researchers mapped the traditions against the bathymetric record, the locations described correspond to coastline features that would have been above water at the relevant periods. Picture a community on a coast, not the polished image of a documentary, but the real thing. The smell of salt and smoke, children playing at the edge of the water, an elder pointing to a spot just offshore and saying, "My grandmother told me there was a path here once." Before the sea came up, her grandmother had told her the same thing. The path is 10 meters underwater, has been for 2,000 years, but the memory of it is still there, passed down through the chain of telling, still pointing at the right place. That is the kind of memory Nunn and Reed have been documenting, and it changes the way we should think about the depths to which human traditions can reach. Here is where the care this chapter promised becomes most necessary. The existence of flood traditions in multiple cultures is real. The evidence that some of them preserve genuine memories of post-glacial flooding is real. Neither of these facts supports the inference that there was a single global flood event corresponding to a specific date, or that the similarities between different cultures' flood traditions indicate a connected historical memory of a single catastrophe. Each tradition needs to be evaluated on its own terms, in its own cultural context, against its own regional geological record. The attempt to collapse the diversity of these traditions into a single narrative of a universal flood goes beyond what the evidence supports, and should be understood as such. What the evidence does support is a picture of human communities as considerably more capable of long-term memory than was previously assumed. Now, Bring this capacity to the sky. The sky changes over time in ways that are calculable and datable. Precession shifts the positions of the stars across the centuries. The communities that lived through dramatic climate shifts and landscape transformations at the end of the last ice age would have experienced those changes as a fundamental disruption of the world they knew, including the world of the sky above them and the seasonal patterns they had depended on for generations. Did those communities encode the memory of what they observed? Did the astronomical knowledge that helped them navigate and time their activities survive the disruptions of the deep past and arrive, in some form, in the monuments and traditions that researchers are now learning to read? The honest answer is that for the most ancient periods, any direct connection between specific climate events and what we find in later monuments and traditions remains speculative rather than demonstrated. That honest uncertainty needs to be stated clearly. The Younger Dryas predates the oldest traditions that have been reliably analyzed for specific astronomical content, and the gap between the two is large enough that caution is warranted. But the question is worth asking precisely because the tools for investigating it are improving. Ancient DNA extracted from human remains is mapping the movements of populations through the disruptions of the late Ice Age and early post-glacial period, showing which communities survived, which were displaced, and which maintained enough continuity to potentially carry accumulated knowledge forward. Sedimentary analysis is reconstructing the environments that ancient communities were living in and adapting to. The picture being assembled from these different research programs is one in which the boundary between the historical and the prehistoric, between the documented and the remembered, is less sharp than was previously assumed. People were paying attention before writing began. They were encoding what they noticed in forms designed to outlast the individual, the generation, and sometimes the civilization. The sky was one of those forms. The monument was another. The story told around the fire at the edge of the advancing sea was a third. None of these forms of encoding is perfectly reliable. All of them are subject to loss and distortion over time. But across the long spans of time that separate us from the oldest human communities, some of what was noticed and encoded has survived. In the solstice light that enters Newgrange every December, in the Venus table of the Dresden Codex, in the directional errors of the pyramids that Kate Spence read as a signature of the precession, in the Aboriginal Australian traditions that describe coastlines now meters underwater, the memory is long. We are still learning how long. Chapter 10. What the software found. There is a moment that happens in archaeoastronomy work with a regularity that has not diminished its power. A researcher sits at a desk late at night. The office around her is quiet. The kind of quiet that settles into buildings after everyone else has gone home. A half-empty cup of coffee sits to one side. Forgotten. On the screen in front of her is a software interface that looks, at first glance, like an ordinary star map. The kind of thing you might use to identify the constellation rising above your backyard on a clear night. The controls are not complicated. A coordinate field for location. A date field. A display that renders the sky as it appears from any point on Earth at any moment in history. She enters the coordinates of a site that has occupied her for months. The latitude and longitude of a temple whose axis has been carefully measured, a monument whose orientation has been proposed to correspond to a specific astronomical event at a specific historical date. She enters the construction date, drawn from the archaeological record, and then she runs the sky backward. The stars drift to their ancient positions. The planets move. The sun's rising point on the horizon shifts slowly as she moves through the seasons of the simulated year. And at some point, if the hypothesis is correct, if the monument was built to capture a specific astronomical event, the sun or the moon or the target star rises at exactly the bearing the monument faces. When that happens, she sits very still for a moment. Not because the software has proven anything by itself, It has not. The match between a calculated astronomical event and a measured monument orientation still requires the interpretive work of connecting them through a chain of evidence that can withstand scrutiny. But because the moment of visual confirmation is the moment when an ancient intention becomes, briefly, legible across thousands of years, someone pointed that, building in that direction, on purpose. And the purpose was this. The software that makes this moment possible has transformed the field in ways that are still being absorbed. Stellarium is an open-source planetarium program that can be downloaded and run on an ordinary personal computer. It can simulate the sky from any location on Earth at any date within a range covering hundreds of thousands of years. Accounting for precession, the proper motion of individual stars, and the changing positions of the planets. It has become a standard tool in archaeoastronomy precisely because its results can be independently verified by any researcher with a laptop and an afternoon to spend. Claims about astronomical alignments that would previously have required specialist expertise to evaluate can now be checked by anyone willing to invest the time. Proposed alignments that do not hold up under independent calculation do not survive long in the literature. Those that do survive generate follow-on research that tests them from additional angles. This is how the field has been raising its standards of evidence over the past 2 decades. And the improvement is real and ongoing. The most significant development in the astronomical tools available to researchers is not a piece of software. It is a space mission. The Gaia mission of the European Space Agency was launched in December of 2013 and has been observing the sky ever since, from a position approximately 1.5 million kilometers from Earth. Its purpose is the construction of the most precise, 3-dimensional map of the Milky Way galaxy ever attempted. As of its most recent data releases, Gaia has measured the positions, distance, and motions of approximately 1.8 billion stars with a precision that no previous instrument has approached. Stars are not perfectly fixed. They move relative to one another, slowly, in what astronomers call proper motion, over the timescales most relevant to human history. This motion is small enough to ignore for most purposes. But for the most precise archaeoastronomical calculations, the ones that require pinpoint accuracy in reconstructing the ancient sky over very long periods, the difference matters. Gaia's measurements are precise enough to allow researchers to reconstruct the ancient sky with a fidelity that was not previously achievable. Picture another researcher. This one, working not at night, but in the early morning. The sky outside his window, still dark. Running calculations for a monument that has resisted confident interpretation for years. He feeds the Gaia-corrected stellar positions into his model. The ancient sky assembles itself on the screen with a precision that earlier versions of the calculation could not achieve. And something in the alignment sharpens. Not dramatically, but measurably. The ambiguity that had kept the interpretation tentative narrows by a degree that changes the weight of the evidence. That is what better tools do. They do not always give you new answers. Sometimes they simply make the existing answers more or less certain. And in archaeoastronomy, where so much has depended on the precision of calculations that older tools could not quite resolve, the difference between uncertain and somewhat more certain is the difference between a hypothesis and a finding. At Göbekli Tepe, excavation continues. Geophysical surveys of the hill have mapped the subsurface in sufficient detail to identify at least 15 additional enclosures not yet excavated. The site was occupied and modified over a span of roughly 1,500 years. The material it contains represents 1,500 years of cultural activity by communities whose relationship to the sky we are only beginning to understand. Each new enclosure whose pillar orientations can be measured adds data to the ongoing analysis of whether the site was organized according to astronomical principles, and if so, what those principles were. In Egypt, the convergence of archaeoastronomical research with new remote sensing technologies is producing a more detailed picture of the tradition of astronomical monument building than was available even a decade ago. Satellite imagery has identified possible astronomical alignments at sites not yet excavated. Ground survey of known sites using modern instruments has produced more precise measurements of existing alignments, allowing older hypotheses to be tested against more accurate data. In the Maya world, the ongoing decipherment of classic Maya inscriptions has continued to reveal the depth and sophistication of Maya astronomical knowledge. Eclipse prediction tables, Mars cycle records, records of specific astronomical events tied to political and ritual occasions. All of these appear in the inscriptional record and collectively paint a picture of a tradition of sky watching as sophisticated as any in the ancient world, maintained with institutional continuity across centuries. Artificial intelligence is beginning to play a role in several of these research programs, though it is important to be precise about what that role is and what it is not. Machine learning algorithms have been applied to the problem of undeciphered scripts and to the analysis of large databases of monument orientations, looking for statistical patterns that human analysts alone might miss. The results so far have been suggestive rather than decisive. The algorithms can identify patterns. They cannot yet tell us what the patterns mean, because that question requires the kind of contextual knowledge about specific cultures and specific periods that algorithms cannot supply by themselves. The combination of computational power with deep contextual expertise is where the most productive research is happening. The software can run the calculations. The space mission can provide the stellar positions. The machine learning algorithms can find the patterns in large data sets. But the meaning of what is found still requires the human researcher who knows the culture, who knows the site, who has spent years learning to ask the questions that the data can actually answer. And then there is the sea. The University of Bradford's Submerged Landscapes Research Center has been using seismic data from the North Sea, data collected originally by energy companies drilling for oil and gas, to reconstruct the ancient landscape of what researchers call Doggerland, the territory that connected Britain to continental Europe during the last ice age and was gradually submerged as sea levels rose over the following 10,000 years. The reconstruction has produced maps of ancient river channels, coastlines, and hillsides that have been underwater for 8,000 years. The territory was habitable. It was inhabited. Bone harpoon points, dugout canoes, and fish traps have been recovered from the North Sea floor by fishing vessels over many decades, alongside animal bones and occasional human remains. All of them evidence of a world that existed above the waterline and that was watched over by the same stars that now hang above the open water. Whether any astronomical monuments built by the communities of this drowned landscape survive in the sediment of the North Sea floor is not yet known. The underwater archaeology of submerged prehistoric landscapes is in its early stages, but the technology for identifying signatures of human habitation in subsea sediments is improving, and the research programs developing it are serious and ongoing. If prehistoric astronomical monuments do exist on the floor of the North Sea or in other submerged coastal zones around the world, their discovery would represent one of the most significant expansions of the known record of human sky watching in the history of the field. The tools are getting better. The questions are getting sharper. And the record of who was watching the sky, and from where, and for how long, is being extended backward into periods that were previously beyond the reach of any instrument we possessed. Chapter 11. The sky is the oldest library. Come back, for a moment, to the beginning, to the ceiling in the temple, to the map carved in stone by hands that have been dust for 2,000 years, encoding observations accumulated across centuries before the chisel ever touched the sandstone, preserving in its layered composition the work of watchers who could not have known that the stone would one day be cut from its ceiling by a French engineer and shipped to Paris to sit in a museum room where tourists walk past it without stopping. They could not have known that. They carved it anyway. That fact is at the center of everything this story has been circling. The people who built the monuments and maintained the traditions and memorized the positions of the stars and carved what they saw into stone were not doing it for us. They were not building toward some future moment of recognition. They were doing it for reasons that made sense in the world they inhabited, within frameworks of meaning that we can partially reconstruct and partially only guess at. For communities that needed the sky in ways that were practical and ceremonial and cosmological all at once. And yet, what they left has outlasted everything else about them. The names of the people who built Newgrange are not known. Their language is not known. Their political organization, their social structure, the stories they told about the world and their place in it. None of this has survived in any directly recoverable form. What has survived is the building. And the building, 5,200 years after it was completed, still does what they built it to do. The solstice light enters the roof box. It travels the passage. It illuminates the chamber. Whoever they were, whatever they believed, they got the geometry right. Think about what it takes to get that geometry right. You need to know where the sun will rise on the mornings around the winter solstice with enough precision that a shaft of light entering a gap of approximately 20 centimeters at the top of a doorway will travel 19 meters along a passage and arrive at the correct location in the inner chamber. You need to know this before you begin building, because once the stones are in place, you cannot adjust them. And you need to translate that knowledge into a physical structure. Working with stone. Checking your work against the sky itself. Waiting for the relevant morning each year to see whether the light is falling where you intended. This is a description of people who knew what they were doing, who had access to a tradition of knowledge that told them what they needed to know, and who executed that knowledge at a scale and with a precision that has not been diminished by 5 millennia of Irish winters. The same thing, in different forms and with different levels of documentation, is true of the pyramid builders who oriented the Great Pyramid to true north with an error of 3/100ths of a degree, of the Maya astronomers who maintained the Venus table with an accumulated error of 2 hours over 5 centuries, of the Babylonian scholars who compiled observations 1,000 years old into the Mull Apin tablets, of the Aboriginal Australian communities who maintained in their traditions descriptions of coastlines that had been underwater for thousands of years. These were not primitive people stumbling toward results by trial and error. They were the practitioners of traditions of knowledge that were, in their own domains, as sophisticated and as carefully maintained as any tradition of knowledge that has existed in the human world. What separated them from us is not the quality, sir, of their attention or the rigor of their observation. What separated them from us is the fragility of the medium in which they stored what they knew. The sky itself is not fragile. It keeps its own record, in the calculable positions of stars, the measurable rate of precession, the predictable cycles of planets, the datable patterns of eclipses. The sky is an archive that does not burn and does not flood and does not require maintenance by any human institution. But the knowledge of how to read the sky, the tradition of watching and recording and interpreting and transmitting, is as fragile as any human institution. It can be disrupted by catastrophe. It can be severed by conquest. It can die the quiet death of neglect that claims any skill that a community stops needing or stops teaching to its children. The Bronze Age collapse that ended the most interconnected civilization the ancient Mediterranean had produced took the Mycenaean scribal tradition with it. Linear B disappeared. The Greeks who came after had no knowledge that their ancestors had possessed a writing system. They did not even know it had existed. The fall of the Western Roman Empire took the tradition of Latin literacy with it in Britain within 2 generations. The engineering manuals sat on the shelves of abandoned villas, as incomprehensible to the people living among the ruins as a technical textbook written in an unknown language. Each of these losses followed the same pattern. The knowledge was real. The tradition was functioning. Something happened, quickly, that broke the chain of transmission. And, once the chain was broken, the knowledge did not survive in any recoverable form. The astronomical knowledge encoded in ancient monuments was more durable than most, precisely because it was encoded in stone rather than in human memory alone. The alignment of Newgrange does not require anyone to remember it. It performs itself every winter solstice. Regardless of whether any living person understands why it was built or what it meant, the directional error of the Great Pyramid does not require anyone to maintain it. It is there in the stone, waiting for the researcher who knows to look for it. But the understanding of what these monuments mean, the context that allows a modern researcher to recognize the alignment or read the error, does require a living tradition of knowledge. The accumulated work of generations of archaeologists and astronomers and mathematicians who built on each other's findings maintained institutional memory in universities and journals and professional societies, and kept the questions alive long enough for the tools to develop that could begin to answer them. We are the beneficiaries of that tradition, and we are its custodians. The sky above the ancient world is calculable. We can look at it from any point in history, at any latitude, on any night. We can watch the sun rise over the heel stone at Stonehenge on the summer solstice of 2,500 years before the Common Era. We can see the light enter the roof box at Newgrange on the winter solstice morning of 3,200 years before the Common Era. We can calculate where the celestial pole was when the Great Pyramid was being built and confirm that Kochab and Mizar formed the alignment that Kate Spence proposed. We can do all of this because the sky kept its record, and because enough of the human tradition of reading that record survived the losses and the catastrophes and the quiet deaths of neglect to reach the people who would eventually develop the tools to read it. That survival was not guaranteed. It was contingent, dependent on specific choices made by specific people in specific moments of institutional fragility. The monks who copied the manuscripts in the centuries after Rome fell, the scholars who maintained the astronomical traditions through the disruptions of conquest and religious change, the researchers who took seriously the oral traditions that mainstream scholarship had dismissed and found in them memories older than anyone had thought possible. Each of them kept something alive that might have died. And what they kept alive made it possible to look at a piece of sandstone in a museum in Paris and ask, with tools that could not have existed without the unbroken chain of preserved knowledge, what sky it was trying to show. The answer is still being worked out. The debate about what the Dendera zodiac encodes, and how far back its observational data reaches, has not been resolved. The question of what the builders of Göbekli Tepe knew about the sky will not be answered until excavations still decades away have been completed. The question of what astronomical knowledge the communities of the drowned North Sea coastline maintained before the sea took their land may never be fully answerable, because the evidence lies underwater, under conditions that challenge every method we currently possess. These are not failures. They are the honest shape of inquiry at the frontier of what is knowable. The gaps are real. They are not empty. They are full of lives that were lived completely, and knowledge that was accumulated carefully, and traditions that were maintained with a seriousness that the scale of the monuments alone should convince us to take seriously. And the tools for closing those gaps are better than they have ever been. LiDAR is revealing cities beneath jungles that nobody knew were there. Ancient DNA is tracing the movements of populations through the disruptions of the deep past. Gaia is mapping the positions of 1.5 billion stars with precision sufficient to reconstruct the ancient sky across timescales that no previous instrument could handle. Underwater archaeology is beginning to explore the drowned coastlines where Ice Age peoples lived and watched the same sky from landscapes now beneath the sea. Every year, the frontier moves. Every year, something that was lost comes a little closer to being found. Somewhere tonight, a researcher is running Stellarium backward through the centuries, alone at her desk, her coffee forgotten, watching the ancient sky take shape on the screen, waiting for the moment when the simulated sunrise aligns with the measured bearing of a monument and a long-held hypothesis becomes briefly, provisionally, confirmed, somewhere tonight, on a research vessel, somewhere in the North Sea. Sediment cores are coming up from the floor of what used to be a landscape of rivers and forests and hills, where people lived and watched the stars and told each other stories about what the stars meant. The cores will go to a laboratory. Researchers will spend months analyzing what they contain. The picture of that lost world will become a little clearer. Somewhere tonight, a brush is moving across a carved surface at Göbekli Tepe that has not been touched by human hands for 11,000 years. What the carving shows is not yet known. When it is known, it may change the question we have been asking, or confirm what we suspected, or open a door to a room we did not know was there. The sky is the oldest library. It does not burn. It does not flood. No empire has ever conquered it, and no catastrophe has ever closed it. It just turns, night after night, carrying in its slow procession the record of every community that has ever looked up and tried to understand what it was looking at. The record is still there. We are still learning to read it. Let your breathing slow now. There is one more thing to carry into sleep tonight. Every person in this story, every astronomer who squinted at the stars from a rooftop in Babylon, every craftsman who climbed scaffolding in an unfinished Egyptian temple, every careful observer in Ireland who waited, morning after morning, for the December light to fall exactly where it was supposed to fall. Every one of them was doing something that had never guaranteed its own survival. They were paying attention. They were writing down what they noticed, or carving it, or teaching it, or building it into stone. And then they were gone. And what they had noticed, and written down, and taught, and built into stone, was still there. Still in the monuments. Still in the clay tablets. Still in the sky above all of them. High, patient and unchanged, carrying the record forward into mornings they would never see. The sky is not arranged exactly as the builders of Newgrange saw it. Precession has shifted the pole. The stars have turned on their slow wheel for 5,000 years, since the last stone of the passage was set. But the light on a December morning is still the same light. And the habit of watching it, of standing in the cold and waiting for what the sky is about to do, that habit has not changed at all. Someone is watching tonight, as someone has watched every night, from every latitude, in every century, since the first human being stood under an open sky and felt, for the first time, the particular quality of attention that the stars demand. We are all, in some way, part of that chain. The chain is still unbroken. The watch continues. Sleep well. Dream of what they saw. Good night.